Good morning to the two of you who are watching. Gonna wait until there are 30 concurrent viewers and then start. I'm gonna send out good morning. I'm gonna send out a remind message. While I'm waiting for people to join. Let's see. I am waiting on viewers. Good morning to everyone who's watching and who arrived promptly. I appreciate that. Waiting for 30 viewers and then I will start. Oh, we're up at 20, waiting for 30. I was watching a episode of Chef's Table on Netflix last night, and there's a new Chef's Table, and it's all about barbecue. And it was about this guy in Australia who only cooks with wood fire, and it looked so good. Made me really hungry. And I'm still thinking about it. And he uses this special technique to dry age his beef. And if you go to a steakhouse, they might dry age the beef for 30 days or something. And this guy dry ages his beef for 200 days. So the meat is basically almost rotten. But somehow that makes it taste better. I don't understand why. Gonna wait. Okay, you know what? I'm just gonna start. Okay, good morning, class. So the first thing I want to do is I want to remind you that the first quiz that I assigned last week is due tonight at 11:59 p.m. Okay. And then I've assigned two quizzes this week, right? One from Tuesday and one for today, and those will be due next Friday. All right. So if you have any questions about any of that stuff, I will be in my office hours from 1:40 to 2:30. So just come to the Zoom room. after this lesson, make sure you go to the Zoom room, and we'll also be watching the Wolfcast. All right, so I'm going to be a little bit unfocused today. I have a pretty bad headache from, I think, the smoke probably, so I'll try my best. Okay, so let's get started. So this is AP Physics 1, September 11th. That is Patriot Day today. And this is period 4. So the first thing I want to talk about is I want to talk about slope in your math class. Okay, and we're going to try to translate this into a more physics language. So if you have 2 points in math that are on a line and you want to use those to calculate the slope of the line, you have, maybe points x1, comma y1, and then you have points x2, comma y2. All right. Whoop. I think I just lagged out. If I ever lag out, what I have to do is I have to restart my streaming software. So if you ever see me lag out, I might just disappear for a little bit and then come back. It's because I'm restarting my software. Okay, so if you have 2 points, x1, y1, and x2, y2, and you want to calculate the slope of the line connecting those 2 points, it is y2 minus y1 over x2 minus x1. That's the slope. Okay? Now, if we want to put this in a more physics language, we might think about this as the final point and this as the initial point. So we could write it as y final minus y initial over x final minus x initial. Okay? But then using the language of physics, final minus initial, that's just delta, or change in. Okay? So we could write the formula as delta y over delta x. Okay? Delta y over delta x. But then we'll go one step further, okay? Because in physics, we almost never have y and x. What we have is something else on the axes. So I will call this the vertical axis, and I will call this the horizontal axis. Okay? And that just leads to less confusion because we're going to be putting all kinds of stuff on these axes throughout the class, and it gets confusing if I call it the y-axis because I might put y on the horizontal axis, for example. Okay, so we can think about the slope as delta, whatever is on the vertical axis, divided by delta of whatever is on the horizontal axis. Okay? So that's how we're going to think about slope. All right. So that's just a little mathematical reminder of what slope is. Okay? So I want to go back to the example I did in the last class. I believe I was talking about being groggy. Okay? Talking about being groggy, and I had drawn out a number line. Okay, and here was x equals 0, and I moved over to x equals 7, and that took me something like 4 seconds, I think, and then I stayed put for 3 seconds, And then I moved to x equals minus 3 in 2 seconds. So I did a sequence of motions. So what we would like to do in this class, we're going to be talking about what's called a position time graph. Okay, and also known as an XT graph. Okay, so what we're going to do is we are going to make a graph, and on the horizontal axis we are going to have time, and on the vertical axis we are going to have position, x. So how you want to label your axes is you want to put the variable for the quantity. Okay, so in this case, the vertical axis has position. The variable for position is x. Okay, the horizontal axis has time. The variable is t. Okay, and then in parentheses, you put the units of that variable. All right, so you put position measured in meters, time measured in seconds. So this is pretty standard in scientific papers. Okay, any scientific papers for the graph, they'll have the variable and then the units that it's measured in, the variable and then the units it's measured in. So what if we want to represent this motion, okay, as a position time graph? Well, at time 0, I started at position 0. So at time 0, I started at position 0. Okay. And then it took me 4 seconds to get to position 7 meters. So, we have 1, 2, 3, 4. Okay. In 4 seconds time, I went up to position 7 meters. So that's this point. And we'll just assume that I did so in a consistent fashion, so a straight line. All right. So that's the first segment of the journey. Now, for the second segment of the journey, I stayed put for 3 seconds. Because I stayed put for 3 seconds, my position number doesn't change, okay? But time keeps on elapsing, and so 3 seconds beyond 4 is going to be a time of 7 seconds. So between 4 and 7 seconds, my position number remains at 7. So it's going to stay a flat line. Okay. And then starting at 7 seconds, I take 2 seconds. So that would mean between 7 seconds and 9 seconds. And I go from position 7 meters to position minus 3 meters. So minus 3 meters is maybe right here. So the graph goes like that. So this is another way of thinking about this scenario, okay, in terms of a position time graph. So now what we want to do is we want to figure out, what does the slope mean? So today's lesson is all about slope of graphs. So what does the slope of a position time graph mean? Well, slope is change in whatever variable is on the vertical axis divided by change in whatever variable is on the horizontal axis. So on the vertical axis, I have position. So it's change in position divided by change in whatever's on the horizontal axis, which is time. So change in time. Now, if you recall from the first lesson that we had, change in position over change in time is velocity. Okay? So the slope of a position time graph is velocity. So this is the first piece of information for today's lesson, and that's really important. Okay, velocity is the slope of a position time graph. Now you might say, well, this graph is actually made up out of 3 line segments, so it has 3 different slopes. That's because there were 3 different instantaneous velocities. So what if I said, what is the velocity at 2 seconds? Okay. Well, if I look at 2 seconds, 2 seconds is right here. 2 seconds corresponds to this line segment. Okay. So that would mean basically the slope of the first segment. Okay. So what I would do is I would use the 2 endpoints of this segment, and I would calculate the slope between those 2 points. All right. So this point is 4, 7, and this point is 0, 0, and I would calculate those 2 slopes. What if I wanted the velocity at, let's say, 6 seconds? 6 seconds is right here, and the line segment that corresponds to that one is this. So I would want the slope of that line segment, and I would use these 2 points. So I would use 4, 7 and 7, 7. All right. This is a flat line, so the slope is 0. That's pretty easy, 0 meters per second. So in particular, if the slope is positive, that means you are going forward. Okay. If the slope is 0, that means you are at rest. Okay. And if the slope is negative, that means you are moving back, meaning in the negative direction. Okay. So that's slope in a position time graph. Now I want to talk about how is acceleration represented in a position time graph. Okay? How is slope represented, or acceleration represented in a position time graph? Well, the definition of acceleration is change in velocity over change in time. Remember how fast you get fast. And we know if we have a position time graph, the velocity is just the slope. So the acceleration is change in slope over change in time. So what does it mean if you have a graph that's slope is changing? It means that the graph has one slope, and then later on it has another slope, and another slope, and another slope, and another slope. So it looks curved. It looks bendy. So acceleration is actually sort of the bendiness of a position time graph. Okay? So whenever you see a graph that is bendy, that means that you have acceleration happening. Okay? So let me give you an example of that. What if I have a position time graph that looks like this? Maybe it goes and then it goes like that. Okay, so this graph is made up out of 3 segments. We have a linear segment right here, which has, so if it's a straight line, there's no acceleration, right? So this segment has a equals 0, all right? So, and then this second segment from here to here is bendy. So this segment has a not equal to 0. In fact, it's a negative acceleration because the slope is getting more negative. Okay, we started out with a positive slope and we ended with a negative slope. And then it transitions to another linear segment. Okay, so that means that the acceleration is 0. All right. Let me give you an example of a pretty common position time graph. All right. What if you were base jumping? You know what base jumping is? It means you jump off of a building or something and then you pull your parachute. Okay. Or no, let's just say skydiving. Let's say you're skydiving. So your position starts out quite elevated, right? You're skydiving, you're in the sky. And you, once you jump out of the airplane, you're going to start to accelerate towards the ground. So you're going to have a bendiness. The graph is going to bend downward as you pick up speed in the downward direction. However, when you are skydiving, you will reach, because of the atmosphere, there's something called air resistance or drag. And what that does is the faster you go, you build up speed, but eventually air resistance becomes so strong that you don't pick up speed anymore. Okay? So you accelerate for a little bit, but then you reach a maximum downward speed. Okay? And so the graph goes from being bendy to being linear. And once your speed isn't changing, you've reached what's called terminal velocity. So it's the fastest you can go through the atmosphere. Okay. If the Earth had no atmosphere and there was no air resistance, then this graph would just continue to bend and you would go faster and faster and faster and faster. But because of the Earth's atmosphere, you reach a maximum falling speed, which for a human is about 120 miles per hour. So if you go skydiving, the fastest you're going to fall is roughly 120 miles per hour. You can adjust that slightly depending on your shape. So if you were doing sort of like a flying squirrel pose where you're falling like this, your terminal velocity might be less than 120. And if you do kind of like a pencil pose like this, you might fall faster than 120 miles per hour. Okay? As far as calculating what is the acceleration of this segment, I will never ask you to calculate that acceleration. I'll just ask you, is it accelerating, yes or no? And you would say, yes, it's accelerating because that's bendy, or no, it's not accelerating because that's a straight line. Okay? However, I would ask you to calculate the velocity as the slope. Okay? There's another graph that we will also use in this class, and that is called a velocity time graph. Okay? Also known as a VT graph. So a velocity time graph, predictably, has velocity on the vertical axis and time. So velocity measured in meters per second, time in seconds on the horizontal axis. So let's go ahead and translate this position time graph to a velocity time graph that represents the same motion. Okay, what is the velocity for this first segment here? Well, it would be a rise of 7 and a run of 4. So the velocity would be 7/4, okay, which is the same thing as 1.75. So for that first segment, the velocity is 1.75, and it just stays constant at 1.75. How do I know that the velocity stays constant for this entire segment? It's because it's a straight line. It's not accelerating. The velocity is not changing, okay? So straight line means constant velocity. So the velocity is staying steady at 1.75 for 4 seconds. Okay? Then, what happens at 4 seconds? At 4 seconds, the velocity becomes 0 because that slope is 0. So what's going to happen is, very abruptly, the velocity will go beep, like that, and drop to 0 for the next 3 seconds. Okay, the velocity drops to 0. And then what about for the last segment? The last segment drops from 10 to -3, so that's, it drops from 7 to -3, so that's a rise of -10. And then it lasts 2 seconds, so that's a run of 2 seconds, to give us a velocity of -5. So what happens is the velocity drops down to -5 for 2 seconds, like that. So that would be the velocity time graph corresponding to the position time graph. All right. So so now, like I said, this lesson is all about slope. So what does it mean? What is the slope of a velocity time graph? What is that going to represent? Well, slope is change in vertical variable, which in this case is velocity, divided by change in horizontal variable, which is time. So the slope of a velocity time graph is change in velocity over change in time. So who can tell me what that is? If you know what that is, type it into the live chat while I draw my next velocity time graph. All right. So I'm drawing another velocity time graph. Very good. Yeah. So the slope of a velocity time graph is acceleration. Okay. So notice we got to be really careful here. And so my advice to you is to always read the axes. Read what is on the vertical axis and what is on the horizontal axis, okay? Why is that? Because if you were reading this graph and you were thinking it's a position time graph, but it's actually a velocity time graph, then you're going to interpret it incorrectly, okay? So you need to read the axes because slope can mean two different things. If it's a velocity time graph, slope means acceleration. If it's a position time graph, slope means velocity. So it's really easy to get confused if you don't look at what type of graph it is. I cannot emphasize this enough. I cannot emphasize how many people get this wrong, okay? So make sure you understand that. So let's interpret this velocity time graph, okay? We've got zero velocity here. We've got positive velocity here. We've got negative velocity here, all right? So I'm going to break this graph into 4 segments. There's segment 1. There's segment 2. There's a single point right here, which I will call point 3. And then there is segment 4, which is that segment. So what's happening in segment 1? Well, segment 1, the velocity is positive. See how it's above the time axis. So the velocity is positive. But the graph is flat right here. Okay? The graph is flat. So that means that the velocity is not changing. So you have a positive velocity that is not changing. So what that means, so I'm going to write that. If I was going to describe this motion, we are moving forward at a constant speed. That's what's happening in segment 1. What about segment 2? Segment 2, the velocity goes from a positive number to 0. So if you're going forward and then your velocity becomes 0, that means you were slowing down. You were going like that, slowing down. But you are slowing down while moving in the positive direction. So this is kind of like you're rolling up to a stop sign. You're moving forward, but while you're moving forward, you're slowing down gradually. Okay? So this is moving forward, but slowing. Okay? What about segment 3? What is the velocity at segment 3? See how the velocity here is 0. So we would say that you are at rest for point 3. Okay. And so you're at rest for point 3, just for an instant. And then I'm going to wait. I want you to type into the live chat if you think you know what's happening in point 4 or in segment 4, this entire segment. So type it in if you know what's happening in segment 4. And so when I say describe what's happening, you're either going forward or backwards, or you're at rest, and you're either speeding up, slowing down, or moving at a constant velocity. So you have 3 options for direction of travel, and then you have 3 options for what's happening to the speed. Is it getting faster, slower, or not changing? So I'll give you a second. Okay, so yeah. So very good. So see how the graph dips below the time axis? So that means the velocity is negative. So that means you're moving back. Okay. And we can see that the number is getting more and more negative. Okay. So negative 10 meters per second is faster than negative 5 meters per second. Okay. It's moving faster in the leftward direction. So this is getting more and more negative, which means you're going faster and faster. So you're speeding up. Moving back and speeding up is the answer. Let me draw two graphs just to illustrate how easy it is to be confused. All right. What if I have a position time graph, and here's the graph? What if I have a velocity time graph that looks exactly the same? But these are very different motions, okay? So notice how if you cover up the vertical axis, those two graphs look exactly the same. But they're completely different once we read the vertical axes, okay? So what's happening in the first graph is your position is negative and it's remaining at the same negative value. So basically this graph represents someone standing still left of the origin. They're just chilling out at x equals minus 5 meters, for example. Okay? This one means that the velocity is negative. The velocity is negative, so that means moving in the leftward direction. Okay? Moving in the leftward direction at a constant velocity. So this graph represents motion. This graph represents being at rest. But they both look exactly the same in superficially. Okay? So I hope that that illustrates to you how important it is to read the graph, read the axes. All right, so I'm going to give you guys a little exercise here. Okay, I'm going to put it on a sticky note. What if I have a velocity time graph that looks like this? Oh, you guys can't even see that at all. You know what? We're just going to do this exercise in the Zoom room. So you know what? I'm going to meet you guys in the Zoom room. I'll see you there in about 1 minute, okay?